Hi everyone, my research topic is extended variational mode decomposition algorithms or developed speech emotion recognition performance. In my presentation, I will speak about the background of the work and the research questions, and also recent works, also our methodology and experiment analysis. To analyze customer sentiments, we have two types of different methods, paralinguistic and linguistic. In linguistic method, which is text-based emotion recognition, source of the data is emails, surveys, customers review, blog and from social media. We applied sentiment analysis through NLP methods to analyze the customer's satisfaction level. Another way is signal-based emotion recognition, which is paralinguistic emotion detection through speech signal processing. Signal-based emotion recognition, we have different methods like biosensing, ECG, EEG signals, and facial expression detections, voice of customers. Analyzing voice of customers is our method, and there are different type of the voice-based analysis. We can use the Fourier transform, which is traditional way, imperial wavelet transform, or variational mode decomposition, which is a new approach. We introduced new algorithms through variational mode decomposition. When we only have voice of the customer, like call center log files, we can apply speech emotion recognition to analyze the customer satisfaction level. In VMD method, we decompose the component of the speech signal and extract the features from the subsignal separately. The novelty of our method is using the dynamic feature vector augmentation and automatic selection of the optimum value of the decomposition parameters in VMD algorithms. Most of the time, the meaning of the word is dependent on the tone, pitch, and loudness of the voice. So during conversation, humans receive a lot of meta information apart from text. This is inherited problem of the text-based sentiment analysis in the NLP method. Motivated by this, two research questions will be raised here. The question one is how to improve paralinguistic emotion detection through speech signal processing. And the solution for question one is we can find the most informative acoustic features from voice of the customers. And the second solution is denoising voice by decomposition techniques and enhancing signal acoustic features data. The second question is what's the role of the data augmentation and signal decomposition techniques to improve the speech emotion recognition. For this research question, we proposed the VGG-optiVMD algorithms, which is a dynamic acoustic feature vector augmentation by extending the existing variational mode decomposition algorithms. Our algorithm can enhance the distinction of the frequencies carries emotion data and improve the emotion classification. There are a lot of other works. They use the voice-based emotion detection, but there is only one work they use VMD algorithms to analyze emotion from voice of the customer. So this is the only research work used VMD to develop speech emotion recognition performance. Other previous works used not a speech signal, mostly used EEG and ECG signals to detect emotion. Here we can see the voice from the RAVDES database, load with 16 kilohertz sample frequency, and used upper energy filter to extract only signals that have higher energy into a series of the frames with 50% overlap. The frame concatenates and creates a high energy input signals for VMD. In the second step, VMD decomposes the input signals to 5 subsignals, which is mode 1 to mode 4, They extract time domain and frequency domain features from mode signals and finally use a SVM classifier. The contribution of this work is increasing accuracy by 12% on Ravdas database by combining MFCCs with 45 spectral statistical features. This combination could improve SVM classifier accuracy. They could achieve 69% accuracy as well. So this is the one work, and the next slide I will introduce our proposed method. A brief explanation about our model workflow. Here we load the voice file with 88 kHz sample frequency and extract the features like Mel-spectrogram, MFCC, Chromagram, and Tonnetz into a multi-dimensional feature maps, and then we apply an oversampling technique to balance the minority classes. These proposed algorithms can enhance informative data in feature maps and boost VGG training process. So these two ability of the algorithms can reduce overfitting problems as well. In first step, we apply initial set of the alpha and ka and change them iteratively. In parallel, we observe classification accuracy until we obtain the highest value of the AUC and F1 score. So when we reach to the highest value of the accuracy or the break loop condition, we set that decomposition parameter alpha and ka as an optimum value. So the algorithms automatically and practically selects optimum decomposition parameter. Before I explain algorithm design, I think I should explain how improper selection of the decomposition parameters alpha and ka can affect the quality of the sub-signals. So here we can see the low value of the alpha and ka parameters cause mode duplicating, and here we can see high ka and alpha value will cause mode mixing phenomenon, and also we can see high ka and low alpha or low ka and high alpha will give us mode mixing as well. So the issue is extraction feature from wrong subsignals don't carry informative information and usually consider noise not a proper data. So this is the drawback of the VMD algorithms. How we can fix this one? We propose our algorithms to select the right value of the alpha and ka. So in the proposed algorithm, the input is pre-processed speech signal converted to the feature vector. The output is the optimum value of the alpha and ka. First we define initial set of alpha and ka, and then we upgrade the frequency baseband. G ka is the spectrum of the feature vector, and we update the central frequency center of the mode with omega ka, and we do repeat this process until we convergence to optimum value of the G ka, and we at the end we could decompose the different modes like G1, G2 and G3. To do that, we need to set some of the hyperparameters is fixed like tau, DC and initial. After decomposition, the signal GT, we go to the second part of the algorithms, which is VGG network is trained on the augmented feature vector to classify emotions, and that's for this we monitor ACC during in each augmentation. We monitor the ACC. If the ACC is max and this condition meets, we will actually define that alpha and ka as the optimum value. So in this way we automatically select the decomposition parameters and based on the converges on the model performance. So the output is a fine-tuned, optimized classifier performance. So we have two data sets. One is bearing EMO-DB, and raw of this data sets for this for our experiments analysis. We used two data sets. Here in this graph, we show efficient functionality of our proposed algorithms on the feature vector 3D Mel spectrogram. So we clearly see a higher distinction in energy magnitude of the frequencies after using this our algorithms. This graph shows before we use the algorithms and after that. So VGG networks can classify this 2D image in the better way. In this graph, we compare the classification accuracy on two different feature vectors, and here we can see it by concatenating the extracted features. We can have better results for both data sets. In this graph, we analyze the effect of the sample rate and window sizing on our algorithms and baseline model. We can see that by increasing sample rate, our model performance is increased, and for a baseline model is not stable. In this table, I wanted to show compare with our work with other previous works, and we can see we achieved the state of the art results with 96% accuracy. Advantage of our algorithms is this is the first study employ VMD as a dynamic acoustic feature data augmentation in SIR and reliable classifier output. The limitation of our work is functional constraint of the VGG-optiVMD due to increasing a heavy computational load when value is over 2000 over 8 and sample rate is over 88 kHz. The conclusion of our study is that there is a synergistic relationship between sample rate and optimum selection of the VMD decomposition parameters alpha and K in the performance of the motion classifier. The finding confirmed the optimum value of the alpha and K are limited to 1 and K for 1 and between 1 and 6 and alpha between 2000 and 6000 on voice of customer-based emotion pattern discovery. The whole process of the VMD voice signal processing is very time-consuming, and for future work needs to be done to establish whether extracting acoustic features only for informative subsignals can reduce computational load constraints or not. The challenge is how to identify informative subsignals. So you can find more experimental analysis in my GitHub in below link. Thank you for listening to